This is part 4 of my lecture on parametric tests for comparing means, in which I'm going to be looking at how to compare a sample with a population with an unknown standard deviation. Here we're testing a sample against a population with unknown standard deviation. If you remember, in the previous part of this lecture we were comparing a sample against a population when the standard deviation was known, but here we don't know the standard deviation. So we're given a population, we know the mean, but we don't know the standard deviation of the population. The data we have available are our sample of several measurements, and we want to test whether the sample could have come from the population with this mean. The statistical test that we're going to use is the one sample t-test. Remember, we used the one sample z-test when we knew the standard deviation. Here we're using the t-test because we don't know the standard deviation. The one sample t-test assumes that we have a population mean, MP, for the yellow population, but we don't know its width, we don't know its standard deviation. But we have a sample of n measurements with mean MS and sample standard deviation SS, shown by the purple distribution. So we do know the standard deviation of the sample, but not the standard deviation of the population. The null hypothesis is that the sample came from a population with this mean, and the test statistic is t this time, very similar to what we had before. T is ms minus mp over the standard error of the mean, but the standard error of the mean this time is defined as the sample standard deviation divided by root n minus 1, where, if you remember, for the z-test we had the population standard deviation divided by root n. So what does this mean? Well, the standard error of the mean, SEM, is an estimate of the precision of which we've measured the sample mean, as we've seen before. But this time, instead of knowing the population standard deviation, we have to estimate from the sample standard deviation. And if you remember from our lecture on sampling, the standard error of the mean was defined as the sample standard deviation divided by root n minus 1 as an alternative to the population standard deviation divided by root n. This time we don't know the population standard deviation, we only know the sample standard deviation, so we have a root n minus 1 in this formula instead of a root n. The test statistic t is the difference between the two means, the sample mean and the population mean, divided by the standard error of the mean, just as we had for the z-test. But because we've estimated the standard error of the mean from the sample standard deviation, rather than knowing it from the population standard deviation, instead of having a test statistic that is normally distributed, we have one which follows the t distribution, and the number of degrees of freedom matters for the t distribution. The number of degrees of freedom is n minus 1. So for small n we have to use the t distribution instead of the normal distribution. But if n is large, more than about 30 typically, then the t distribution and the normal distribution are about the same, and it really doesn't matter which we use. So the recipe for the one sample t-test is calculate the mean and standard deviation of the sample measurements, take the difference between the sample mean and the known population mean, estimate the standard error of the sample standard deviation. So the standard error of the mean estimated from the sample standard deviation is the sample standard deviation divided by root n minus 1. Then we divide the difference by this standard error, which gives us the test statistic t, and we look up the critical value of t from a table of the t distribution instead of the normal distribution, and the number of degrees of freedom that we have to use is n minus 1, the number of measurements in the sample minus 1. Then if t is greater than the critical value determined from the table, we can reject the null hypothesis in the normal way. So let's have another example. Once again, we'll use the data that we saw in the previous test about the IQ of lecturers. So our question is still the same as before. Do university lecturers have above average intelligence? And we had an experimental hypothesis that lecturers have higher IQ than the average population, and the null hypothesis is that lecturers have the same IQ as the average population, and we decided that was a one-tailed test because we're only interested in lecturers having a higher, not lower IQ. The data is exactly as we had before. An average population has an IQ with a mean of 100. Last time we were given that the population standard deviation was 16, but this time we're not going to make any assumptions about the population standard deviation, so we're going to assume that the population standard deviation is not known. We've got the IQ of the sample of 4 lecturers exactly as we had before, 110, 104, 114 and 120. The statistical test, as before, we've got some quantitative data. We know the population mean, but this time we don't know its standard deviation. So instead of using the one sample Z test, we're now going to use the one sample T test. Here is our data, the lecturer's IQ shown by the 4 dots, and this time I've just put a line at 100 for the IQ of the general population without any error bar, because we're not assuming any standard deviation for the known population. So once again, do we think that lecturers have above average IQ? Well, as we said before, it looks like they all lie above the mean. We've already calculated that the total IQ was 448 with a sample number of 4. That gives us an average of 112 for the average lecturer's IQ. To calculate the standard deviation, we have to take the difference between each of these IQs and the mean to give the deviation from the mean. The mean is 112, so 110 is 2 below the mean, 104 is 8 below the mean, 114 is 2 above the mean, and 120 is 8 above it. Note that the sum of all those deviations adds up to 0, as it should. To calculate the standard deviation, we have to square those deviations. Minus 2 squared is 4, minus 8 squared is 64, 2 squared is 4, and 8 squared is 64. So if we add up all those squared deviations, we get a total of 136. Now, the variance is defined as the mean squared deviation. So it's 136 divided by n, which is 4. 136 over 4 is 34. That's the sample variance. The sample standard deviation is going to be the square root of the sample variance. The square root of 34 is 5.8. So that's our sample standard deviation. The formula for t is the ms minus mp over the standard error of the mean. We know that ms is 112, we've just calculated that, and we just calculated ss, the sample standard deviation, to be 5.8. mp, the population mean, is 100, we are given that. We need to calculate the standard error of the mean. The standard error of the mean is the sample standard deviation, 5.8, divided by root n minus 1, which is root 3. So that comes to 3.3. Notice that we used n minus 1, root 3, rather than root n, because we are estimating the standard error of the mean from the sample, rather than knowing it from the population. So t is the sample mean 112 minus the population mean 100 divided by the standard error of the mean, which is 3.3, and that comes to 3.6. So we need to know whether this is significant, and first of all let's note that it has a positive sign. So if t is positive, that means that ms must be bigger than mp, so at least our sample mean, our IQ of our lecturers, is greater than the population mean, 100. So it's in the right direction. The number of degrees of freedom is n minus 1. n was 4, so the number of degrees of freedom is 3. So we have a t of 3.6 with 3 degrees of freedom. The t distribution is a little bit more complicated than the normal distribution because we have to take into account the number of degrees of freedom. In the table here there is one row for every different number of degrees of freedom. We're interested in 3 degrees of freedom, which is this row, and if we look, we've got 2 values for p, a one-tailed and a two-tailed. We're interested in the one-tailed test, and for p equals 0.05 one-tailed we have a critical value of 2.353 for 3 degrees of freedom. That is the critical value. And for a one-tailed P of 0.025, we have a critical value of 3.182. So those are the values we're interested in, 2.353 and 3.182. So from this table of the T distribution, with 3 degrees of freedom, a significance level alpha of 0.05 in a one-tailed test, we've seen that the critical value is 2.35. If you remember, we had a value of 3.6. So it's more than the critical value. Because it's more than the critical value and it's positive, that it's in the right direction, we have a significant result. We have a significance P of less than 0.05. In fact, it's also less than the value for the significance level of 0.025, where the critical value was 3.182. So 3.6 has exceeded that as well. So it's also significant with P less than 0.025. So we can reject the null hypothesis in this case, and we conclude that after all, lecturers do have above average IQ if we use this test where we estimated the standard deviation rather than assuming the population standard deviation. So depending how you look at it, either lecturers do have above average IQ or maybe they don't. So that's the end of the fourth part of this lecture on comparing means.